Okay, just as a quick review, last time, was it last time or 2 times ago, we talked about the IEEE 754 standard last time? Okay, so 2 different ways of representing single and double precision floating point numbers. So in Java, this would be a float. In Java, this would be a double. So we split it apart. We wrote an algorithm for actually doing this, right? We wrote the code in Eclipse, I think. Did we write all of that? Oh, so we were in the middle of writing the multiply piece. All right, so let's get through the rest of the slides real quick just to bring us back up to speed with that, and then we'll finish that up. All right, so we saw that we could split this apart. We have our exponent piece, the sign bit, and the fraction, and I think we already are dealing with that. Here's S754 to bin, blah, blah, blah. So we have that whole piece, and then we wrote subtraction in terms of that. All right, hexadecimal addition, we'd already done that. Multiplication and division, we talked about those a little bit last time, that they're very time intensive, so we need some trick to speed this up. So we talked about bit shifts, moving to the left, moving to the right. So a left bit shift is a multiplication, a right bit shift is a division, and that works for powers of 2. So for example, we can see the shift go this way. So a 9 times 2 is an 18. So we shift everything to the left, add an extra 0 onto the front. We see that the 9 from this first number goes to an 18, which is the second number, just by shifting it to the left. Similarly, if we want to divide by 2, we shift it to the right, and we're back to the 9. All right, so that's the bit shifts, and we wrote that last time. So here's our left shift, and here's our right shift. There actually is a shift value in Java. So if I say system.out.println 18 shifted to the left 1, oh, I got another error in here. Let me just make this return an empty string for the time being. That's a right shift. That's a left shift. So there's the 9. So in Java, greater than does a left shift this many times. So if I want to multiply it left shift twice, we're dividing. So 18, actually, how do we get a 4? Divided by 2 is 9, divided by 2, oh, because it's not a whole number. So that's how integer division works. Similarly, right shift goes to 72. I'm not sure how often you use things like this, but they do exist. Okay? So those are 2 new operators for Java if you ever run into a need for them. Okay, that was the shifting. So multiplication for non-powers of 2. So for instance, 9 times 5 is a 45. We decided we needed to find the greatest power of 2 less than our multiplier. Really less than or equal to our multiplier, right? All right, so that's where we left off in our code here. We have a little comment, figure out what the largest power of 2 is that is less than the multiplier. So if this is our binary number, and this is our multiplier, and our multiplier, as of right now, I guess is coming in as a string. How did we decide we were going to do this? Is there a reason we took this in as a string? I think we decided we were going to convert it back to decimal. That way we can have binary numbers multiplied by binary numbers, right? Okay. So we'll go ahead and find a power of 2 such that, actually it could be interesting. So we want to do it in binary. If I have a binary number, like for instance the number 5, let's just add the slide real quick. So this is the 4's place, 2's place, 1's place. So that's the number 5. If I give you that binary number, how can we figure out what the largest power of 2 is that is less than or equal to that? Is there a trick we can do that besides converting this to 5 and then figuring it out in decimal? Is there a way we can use the binary to figure it out? Go ahead.
Left shift until you have a 1.
Okay, left shift until you have a 1. Okay, so 1, 0, 1. We left shift that. What do we end up with?
Does it go 1?
Well, you want to left shift it, right?
Yeah.
So everything's going to go over. So the 0 is going to move there, and then we get a 0 there. Or do you want to right shift it?
Right.
Okay. So right shift it. We get a 0 added onto the front, and this guy disappears. Mm-hmm. All right. So we just right shifted once, correct? Okay. Then you want to do it again? Yeah. Okay. So we're going to right shift it again. So we'll add another 0 here. But with that, so now it's 2. We did that twice. So now we know we're done because we have a 1. Okay, so but we did it 2 different times. We right shifted twice until we got a digit of a 1 here in bucket length minus 1. If we're dealing with this in terms of strings. What is that 2 used for?
How many times you need to shift the button number?
Okay, so 2 gives us the number of times that we need to, if we're doing multiplication, left shift the number, right?
Minus 1. Because you've done it 2 times, but you actually need to do it.
Well, we've right shifted it twice. All we're trying to solve for right now is what the largest power of 2 is that is less than the multiplier. If our multiplier is 5, largest power of 2 is 4. So we just counted 2 right shifts. 2 times 2 to the 2 power is 4, right? Does that work out for everything? Let's say I have, let's give ourselves a different starting value. So this is what, 1s, 2s, 4s, 8s, 16s, so that's 24, 28, 29. So this is the number 29. What should be the largest power of 2? Less or equal to 29? Be 16, right? 30. Huh?
It's 27.
Is it? This is the 1s. This is the 2s. 4s, 8s, 16. 16 plus 8 is 24 plus, oh, this is 2s, 27. So, still the same answer. Greatest power of 2, less than or equal to 27? 16, right? 30, next power 2 would be 32, that's not less than it. So we need to get to the 16. So you want to right shift this guy. 1, 1, 0, 1, 1. So we're going to right shift it once. That's 1. Twice. That's 2. That's 3. That's 4. What's 2 to the 4th power? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Okay, so the number of right shifts until we get to a 1 seems to give us the power of 2 that is less than or equal to our multiplier. All right, so if we have that, what can we do? So now we have a number that we can then use to left shift the first number by to get us part of the way towards our multiplication for fast multiplication. Correct? All right, so let's start off with that. So we have our multiplier. We're probably, well, we already have our right shift that doesn't destroy our multiplier, right? So we can say let's actually do this. String temp is equal to multiplier, just so we can deal with it the first time. While temp dot char at temp dot length minus 1 is not equal to a 1. I'm sorry, that's not going to work. We need to make it such that it's only equal to 1. And it's all zeros and a 1. That's the best way to check for that. We can't just look to see if this guy's a 1 because we might have a whole bunch of zeros. Well, I guess we could use our built-in function. So we can say while integer dot parse int temp in base 2 is not equal to 1. So we'll convert temp from a binary representation as a string into its decimal equivalent in base 2. While that's not equal to just a 1, we need to keep track of a count. So count will start off at 0. We'll set temp equal to test dot right shift temp, then count plus plus. All right, so when this is all said and done, count will be equal to the number of times we had to right shift until it became a 1. So we can go ahead and test this real quick. Just to make sure we've gotten that part right. And I'll return an empty string. So we'll say test dot multiply. Doesn't really matter what the first number is for right now, but our second number, we're going to do our 101, which is our 5. And this should print out a 2, right? And then we'll have a test dot multiply. Doesn't matter what that number is. 1, let's see, I want a 9. And that should give us a 4. If we're doing our counting correctly. 2 and 4. All right. So all we solved for right here is the number of left shifts we have to do to our bin to get us at least part of the way down the road. Okay. So in our example here, if we're doing, let's do 10 times 5. So this is the number, 8s, 4s, 2s, 0s. So this is 8 times 5. Get rid of this stuff down here real quick. We already calculated count will be equal to 2. That's the number of left shifts we can do to our 10 here to get us at least part of the way through the multiplication, right? So we have 1, 0, 1, 0. We're going to left shift that. So that gets us an extra 0 here. Kills the 1. Left shift it again. All right, so we just left shift count number of times. And now we're at 1, 0, 0, 0. So that gets us part of the way to the multiplication. What do we have left? Well, we need to do it 5 times, right? I've already done it. Well, we want to multiply a total of 5 times. I've already multiplied 4 times. 2 to the 2 power. So I have 1 left over. What do I do with that last 1? I've done all the multiplication I can. We can add. So you're going to suggest the same thing? Okay. Anything else we can do? Can I multiply again? It's a 1. What power of 2 is a 1? 2 to the 0th power. That means don't left shift. Well, that's not going to get us the right answer. Is there any way around adding? Which is more expensive as far as what we've looked at so far? Adding or multiplying? Certainly we see limitations with multiplying. But doesn't multiplying seem pretty easy? When you deal with this left and right shifts, as long as we're working with powers of 2? So is it a big deal to add once at the end? Let's look at a more complicated example. Let's say I was doing, what was my second value was 11011. So that was a 9, right? And let's say we're doing, no, that's not 9. This is 1s, 2s, 4s, 8s, 16s. Okay. So let's say we're going to do 1010 times that, which is an 8 times a 1s, 2s, 4s, 8s, 16. So that's 20. That's 27. So that's 8 times 27. We decided that the biggest value for that was count is 4, correct? And our code already produces that. So we know that we can left shift this guy 4 times. Well, we're going to run into a problem here. When I left shift it, that's going to be 1, 2, 3, 4. 1, 2, 3, 4. How do we prevent that? We just lost precision. We need to use a bigger base register. So maybe use a 16-bit number. The 16-bit representation of 10.
Are you still thinking that 1010 is 8?
Or don't I keep doing 10? I keep saying 10 but writing 8.
Yeah. I'm like...
Yeah, I'm sorry. I do keep saying 10, don't I?
It's just like
Hold on, we decided that aliens were base 8 a while ago, didn't we? I'm just doing quick conversion, people.
That's your home range?
Yeah, it's my own. Yeah, something in there. I don't know. I kept saying 10. I don't know why. I must have written 8 one time and whatever.
If you're an alien, does that make the hot tub your birthday?
That's pretty creepy. the larva. Well, I posted online. I remember there was when I got the hot tub, there must have been like a dead animal in there. I don't smell it anymore, so I'm pretty sure the maggots have finished.
Wait, so they're not giblets on your back. It's your spawn.
What? It just took a turn. All right, back to binary. All right, so in any case, this is an example of where we need to be careful running out of register space if we're dealing with this at the hardware level. So if we're going to work with values in a certain range, so think about like 32-bit, well, if we think about chars in Java, 16-bit unsigned values, that's the easiest way to depict this. We're going to need 16 zeros and ones to represent this. So our 1010 up here actually is going to be stored like that. Similarly, it'll be stored like that. If we're going to left shift it 4 times, we look like that. So we're able to left shift within its own space, as opposed to losing precision by shifting outside of the register size we're working with. Kind of make sense? So this kind of shows us at a somewhat hardware level, as we're starting to segue towards hardware with logic gates today, that these are things we need to consider in terms of the amount of data we're actually storing. Okay? And also why computers can't be of infinite precision. Okay, so now we've left shifted a bunch of times. So at this point, what we've accomplished is we've multiplied our 10 by 16 in this second example. What we've done is we've multiplied our 10 by 4 in this first example. Make sense? So we already saw that we can now add our 101 to this one more time to get our final answer. Correct statement? But down here, we have 11 more times that we need to add it. Well, how do we do that? I have one more time. I need to add that. 1 times this is what? Is this. So we're going to add. We're going to add 1 times that to this guy. For this guy, I want to add 11 times that. Correct? To get my final answer. Is there a better way of figuring out 11 times that? What's the greatest power of 2 less than or equal to 11? 8. So how many times do we have to left shift an 11 to get us to a 1? So that should be 2, 4, 8. 3 times? So in that example, I'm going to kind of draw the picture here. We're going to put this guy on hold. Actually, just let me get rid of that, because I think you see where we're going now. We're going to put that on hold, and we're going to call our method. Hold on, I did the wrong thing there. We're going to call our multiply method again. Count starts off as 0. Again, this is going to be, we're doing this all as 16-bit just because that's what we decided on. So now we need to right shift this some number of times to figure out, oh, am I lying? I am lying. We have 11 left. All right, that's 11, right? I need double checking. 8, 9, 10, 11. I need to right shift this some number of times until I get to a 1, which should be 3 times. Okay, so I'm going to pass in my 11 because I'm going to be multiplying it by 11. That is this number times 11. All right, so the secondary math we're doing is, if I steal this, just to paint the whole picture, is that number as the multiplicand, and that number. So this is 27 times 11. All right, so we're going to right shift this some number of times. That's going to get us what? So we're going to shift, shift, shift 3 times. Now we're looking at our 1. Count will now be 3. So now I know that I can left shift this number 3 times. Correct? So let's get that number down here. So I'm going to left shift this 3 times. 1, 2, 3. 1, 2, 3. So now it's this number. Now if we're adding this to our stack, if we want to visually see what we're doing here, these are our multiple calls to our code. But just down here, what I'm going to do is I'm going to just start creating something like this. So we can add these 2 numbers together, right? So now I've done times 16 times 8. What do I have left? 3? Okay, so I need to take this number. I'm sorry, not that number. I need to take this number times 3. We got it times 16 here. Got it times 11 here. Well, try to do it times 11 here. Got it to times 8. So I have 3 left. So I can either add this guy on 3 times and be done with it, or I can multiply this again. So now I can make another call. These are recursive calls. And now I'm multiplying by 1, 1. That makes it look a little nicer, 0, 0, 1, 1. So that's 27 times 3. Count will start off at 0. Here, we'll move these guys up top here. All right. Now, how many times do we right shift this to get us to a 1? 1 time. So count will become a 1. So I can take this guy. Oh, that wasn't what I was looking for. We'll left shift him once. Then we have 1 more value to add to our add stack. Notice I keep calling it a stack. All right, so then we were trying to multiply by 3. We just did it by 2. 3 minus 2 is 1. So when we get down to 1, what do? We know that something times itself is a something, so we can just do that last add. So we'll take this guy So there's our 4 recursive calls. This was our end case. Think of this kind of like doing the recursive version of factorial, where we stop when we get to a 1. So our stop case for this is we're going to keep doing the same exact algorithm over and over and over again until we finally have a 1 left for the number of times we need to multiply. That's our final add. We don't need to do the math for it. Okay? Now we add all these together. I guess let's just do the math and we'll... So 1 plus 0 plus 0 plus 0, that's going to be a 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 plus 1 is 1. This just seems fraught with danger. Carry the 1. 1 plus 1 plus 1. Okay, we got to do this as separate pieces. This is what we're going to do. Can I use my own code? We wrote add, didn't we?
Does Mac not have a binary calculator?
It does.
So you just
Yeah,
do more work.
I can add base. I rewrote it. Test dot add base. Pass it our first string. It's going to be a power of 2. And pass it our second string. Which is this guy. All right. Test dot add base. This guy. Added to this guy, base 2. Test dot add base. What don't you? What do you hate?
So ugly.
Oh, it's gonna be perfect. We're gonna see a power of our code. Did I do it all? This guy now, right? There we go. So this should add all the numbers, right? So here's that's our first add. The result of that we're going to add to this. The result of that we're going to add to this. And then we're going to print that out. So there's our answer. We're going to test it. Oh, hello. It's an invisible ink. See? And this is to scale. All right, perfect. Now, this should be what, the number 270? Is that what this ultimately should produce? So, of course. Well, is that in converter dot
Yeah, it doesn't convert to anything that you want to.
binary to decimal? Oh, does it read in? Or does this just not give us the right answer?
No, it's not the right answer.
Are you
at
sure?
all. Yeah.
Yeah, that's the one where it takes input.
Oh, so we're going to have to use the integer dot. Okay, so that value, comma 2. Ruh-roh, okay, hold on. Hold on.
This is what you get.
We got this. So that closes that one. Comma 2, that closes that one.
And then,
One more.
Oh, then one for the print line.
Yeah.
There we go.
This looks like a mess.
Ruh-roh. Do we add the wrong numbers?
no, the numbers are right.
Numbers are right, but our addition's wrong?
No, the addition's right. You just something's wrong.
Well, it shouldn't be wrong. If it's wrong, you guys made a mistake. And I was obviously testing you. All right, well, let's start off with this. So this was 10. Well, no, that's this number. Left shifted 4 times. 1 0 1 0 1 0 1 0 4 times. So that should be right. Then we're adding to that. So that's our original base. Then we're adding to that this number. So we have a kind of a new math. Now we're doing 27 times 11. Right? So we're going to left shift it 3 times. So 1 1 0 1 1. Left shifted 3 times.
Did you go out one too far on that one?
2 1.
One too many? No. I don't.
No, it should be 3 times. 8. The 8th place.
Because even if you add those bottom 3 up, you still get too high of a number.
Shouldn't that bottom should that be 11 times?
Oh, yeah. We had to do the same thing we did up here. So we had this number times yes, this number times 27 times 11. So this one down here should be 11 times 3. So that's 1 0 1 1. 3 is this guy, which matches our pattern. That's 11 times 3. So we're going to shift this value. So this is the value that's different. So we should be able to come in here, fix that guy. Uh-oh.
Did that go up?
It did go up. All right, what are we doing wrong? Do we use too big of an example? Let's go back to our smaller example.
Okay.
It's clearly, this one is too complex. All right, so we decided we were doing 10 times 5. That was our original? Is that right? All right, that's the number 5, right? All right, so 10 times 5. We should be able to do this in decimal and have it work out. So we're just doing the exact same thing. So if we do 10 times 4 is 40, plus one more 10, that's 50. Oh, I think I see what we did. We were doing one more of these guys, not one more of these guys. we were doing the multiplier, not the multiplicand. So here, we should be able to see it in this. All right, so first thing we do is we figure out what our count is. Ugh. This should be a 3. I hate you people.
Okay, you can go and breathe later.
All right, so greatest power of 2, that's 2 to the, this should actually only be 2, right? Count as 2. So count as 2, so we're going to go ahead and we're going to left shift this number twice. Okay. Then we're going to add to that, because we're going to keep doing this until we hit a 1. So we'll make this a little bit more complicated after we see this work. So now we're going to, and actually we can even do, so this is our original number. That. We know that count is 0, so we're not going to shift at all. So we should be able to add these two numbers together, and they should give us one, two, three. Oh, hold on, I converted it back to, oh. So this is the end of our test base, comma 2. There's our 50. All right, this works. I was trying to trick you the first time around, nobody caught it. So let's go back to our more complicated one and do it more better. All right, so here's our first left shift. So we had 10 times 27. We were able to do 10 times 16, right? Next time around, we need to do 10 times 11. Let's see, 8. All right, 10 times 11. We know that count, copy and paste for safety. This would be where you say right leg clearance. another, yeah. Yeah, we'll collect completely unrelated. Right. What's up?
Did you say right leg clearance?
Yeah,
Oh, okay.
he started just incorporating it into normal, just vernacular.
That's back.
Like, oh, yeah, I'll see you later, like right leg clearance or something. There's an inside joke there, by the way. What's up?
It's been a long time since I.
Did you heard that?
Yeah.
Right leg clearance.
You have all these people that aren't in the know. Like, what the heck are they talking about? Alex is back there just in awe. I don't even know what's going on. All right. So now we have 10 times 11, but we know we can only get an 8 out of this, right? So that's going to be our count as 3. So we'll take this value. And we'll left shift 3. Okay. Now we know 11 minus 8 is 3. So next time around, same starting number times 3. This. And we get a count of 1. So we'll left shift 1 time. Okay. Then call it 1 more time. This time we're going to do a 10 times 1. That's 3 minus 2. So this is our 2. 2 to the first power is a 2. 3 minus that gets us our 1. We know that's a count of 0. So we can either look at that or look at this. So we're not going to left shift at all. We're just going to leave it. Okay, now this number plus this number plus this number plus this number should be a 270. Did we decide if there is a binary calculator? So we'll take this number. Yep, that's fine. Add to it this number. Add to it this number. Oh, heck. Oh, we're in base 10.
Oh dear. Oh dear. Oh dear.
Hold on, we can't even select binary?
So does not.
I can't enter stuff in as binary?
That sucks. It's embarrassing.
It sort of is. All right, we're going back to our own code because that's the only thing that's reliable.
You can do this in Windows 95. Come on.
A lot.
Huh?
Why don't you just click?
Because I had lost my original magic where I had all of them nested. So I got to start that again. So we're going to print out integer.parseInt.
Can't just control Z and bring
No, always gotta write it. No, no, that's not fair.
Is that it? All right. There's that value. There's that value. There's that value. There's that value.
Hey.
Worked. All right. See, I was tricking you the first time. So that's fast multiplication.
That was super fast.
I think we can all appreciate under the hood, even though this is proof why we don't use binary as our normal counting system. Okay? I think we can all appreciate that doing left shifts like this to solve the full problem wasn't bad, right? We just kind of sucked as humans making the errors, and by we, I mean you, because I was purposely tricking you. As usual. I don't even know why somebody didn't stop me as soon as I flipped these two numbers.
Yeah, that was impressive.
I mean, it's bad enough that I was calling an 8 or 10 and 8.
We like to see the struggle.
What's up?
We
Like to see the struggle? Yeah. I might add a couple of questions to your homework assignment. All right. So, got a few minutes. Let me just make sure we've covered everything else that's on the homework assignment. Okay, well, let me just talk about this slide real quick because that'll cover everything that's on your assignment. Then we'll code this guy real quick. So this idea of whether something has an arithmetic overflow or not. An arithmetic overflow error occurs when two numbers are added and the result falls outside the valid range of the binary representation being used. So it's important that you notice that difference. We're not talking just that you have a final carry. We're talking that the value, because you have that final carry, and the final carry will always work out for you if you always pad out the values like I've been doing here. Does that make sense? So if you're working with a 16-bit unsigned number, and you always deal with it in full 16-bit resolution, if you will, with all the padded zeros out front, then if you have that extra carry bit, then you could always say that's an arithmetic carry. If you're not working with it in 16-bit chunks, instead you're just working with it in like the larger of the two numbers or something like that, having that carry bit doesn't necessarily give you the information as to whether it's an arithmetic carry. So an arithmetic carry means that your destination register, the destination location where you're putting this, cannot hold the value you're trying to put in there. It's too big. Okay, like putting the number 200 into a byte data type in Java. That makes sense? So in your homework, when it talks about arithmetic overflow, that's what it's talking about. When adding two numbers together, is the resulting number too big for the final destination? Okay? Does that make sense? So questions about that one. So not really a hard concept, just more of a, I don't know, factoid that you'll need for the homework assignment. Okay, and that should be everything that you need to finish your homework assignment, which is due on Thursday, and that's up on Angel. Hopefully most of you have already started it, or at least might even be more than anybody finish it. You might have been missing a couple of pieces, but you probably could have done at least 13 or 14 of them, I would think. Okay, so that's everything you'll need for the homework. Go ahead.
Should we go over 9 and 10 in class? Like, do we learn how to do that?
Well, that's a good question. If the answer is no, then the answer is yes.
Yeah, 'cause I didn't remember about that either.
Oh, this is doing the inverse of our IEEE. It's doing the inverse of this. Let's see. So your final answer might look like something like this, but oh, still did you get it? Can you actually take the inverse like that?
Really?
You need your laptop anyways.
Hey, he owes you one, Evan.
Breaking my laptop.
Well,
Break the legs.
I bet you the laptop costs less than his surgery.
Oh my god, the surgery was fucking expensive. Buy 20 laptops.
Not exactly in a state of mind.
Trying to decide what's the best.
Able to
I don't know if I have time to.
What's
Okay.
soda by now?
All right. It is the inverse of that other thing. So this portion of it is the inverse of the IEEE standard. Then you have this value that helps flesh out the rest of the left-hand side. Trying to think if there's. You can't just convert what's before and what's after. That won't give you the right answer.
Like with powers of 10 is what I'm saying.
With powers of 10.
Well, because isn't that what, it's got that exponent, right?
Mm-hmm.
So isn't,
From our slides here.
I guess I'm saying like
What grade you?
10.1, I don't know.
Well, but you got to keep in mind the number that's on the left-hand side of the decimal point is it's a scalar off of this for positive numbers. Because we get our plus or minus for whether or not this particular example ended up being a minus because we had our sign bit. But so this 1 isn't the sign bit. This 1 represented that this was a negative. So the actual value here, forget about this negative or positive here. The actual value here, the 1, becomes the base for what comes after the decimal point. But this guy is a scalar. Well, I guess this guy would have been the scalar. This part of it would scale off that 1. So it's 1 times the rest of this to get you what's on the left-hand side of the... So this would be a positive this times the whole number this. I don't know if I'm explaining that very well. So if we just take this piece, let's work backwards off just that piece. So we'll solve, what we'll just do real quick is we'll solve 9. That way you'll have to do 10. Fair enough? So I'm about to give you the answer to 9. So let's put it in a new slide here. All right, so if we work backwards from this, this is a positive number, right? Okay, and we know the whole thing was a positive number. So we can right off the bat say our sign bit is that. So that's our sign bit. The exponent part man, I can't have you do it this way. That's going to break it. I haven't taught you a part of this that you need.
Well, it looks like we can't do the homework.
No, you just can't do those two. Trying to decide if I can explain it quick enough rather than just giving you the answer to 9 and just say do 10 the same way. Let's do this. On the homework assignment, skip 9 and 10. Here, I'll edit the assignment. But what I'm going to do is I'm going to leave in the assignment I'll teach you how to do it in class when we go through the solution, because it's going to take probably 20 minutes or so to kind of go through what this representation is actually, what it actually is. So I'll just add to the assignment. Note, skip numbers 9 and 10 we will do in class. All right? Because I really can't have you do it as a scalar, because it'll be in the wrong format if we try to go back to the exponent thing. We're going the other direction. It's a different algorithm. All right. Now I think you have everything to do, everything that you'll need for the homework assignment, except for 9 and 10. All right. Now, quickly, if we have our multiply method that's going to take our binary string by the multiplier, so in our example code here, or example text, this is the bin, this is the multiplier. Okay? Now, realistically, if we really wanted to do this as fast math, we would flip it so that the smaller of the two is the multiplier. That makes sense? But we're not going to do that in this case. We just want it to work. We can certainly compare them pretty quickly. All right, so this is bin, this is multiplier in this code. Bin, multiplier. So the very first thing we do is we find out what is the smallest value of 2 less than or equal to multiplier. So what we probably want to do is we probably want to turn that into a method, because that's something we're going to have to call fairly often. So we're going to say static string largest power of 2. We'll pass in a multiplier. I'll just steal that code there real quick. Okay, we'll leave that alone. So this guy's going to take in a multiplier. We'll set temp equal to that. Start count off at 0. Keep spinning through right shifting, counting the number of times we had to right shift until we finally get to a count. Let's actually have this guy return a... We'll have it return an int so it matches our example code. Thank you. All right, so we can call this whenever we need to find the largest power of 2 greater than or equal to a multiplier, or less than or equal to a multiplier, sorry. All right, so first time through, well, first of all, let's look at this. We're going to keep doing this over and over and over again until multiplier is 1. Okay, when multiplier is 1, we're just going to add that final value onto our running total. Okay, so whatever we're going to do in here, we're going to do while integer dot parse int multiplier base 2 is greater than 1. So this will only work on positive numbers initially, but good enough for what we're trying to accomplish. Okay, so as long as our multiplier is greater than 2, we need to find the greatest power of 2. So we'll say int curpow is equal to test dot largest power, and we're going to pass it multiplier. We're going to end up replacing multiplier here in a second because we don't want to keep changing our multiplier. We probably want to have another variable. Let's do it this way. Let's call it cur mult. This cur is multiplier. Then we'll pass in cur mult into our parsant here. And we're going to keep updating cur mult. That way we don't change our original here. Okay? Realistically, we're going to end up calling this recursively, so it won't make a difference. I'm going to end up just talking through this because we're not going to have time to finish it anyways. So what we're going to end up doing is we're going to keep going through as long as it's greater than 1. Now, realistically, this won't be a while loop. We're going to take advantage of recursion here to keep calling this method over and over and over again until we finally get if it's equal to 1. We are done, so do the final add. Else, do as much multiplication as possible. That's the kicker in there, right? Okay, and doing as much multiplication as possible means taking our current number and adding it to what multiply does. All right, so if cur mult is not equal to 1, or if it is equal to 1, we're done. We'll do one more add. So we'll just say return converter dot, is it in test or add? Test dot add base. Well, we actually have add bins too, right? And we'll pass it bin, and we'll pass it, we can do multiplier. So that'll be our final add, and we'll just return whatever bin was added to our multiplier one time. Okay? Otherwise, we need to multiply and then add whatever's returned by multiply. And how do we do that? We do that by left shifting some number of times. How many times? Well, we need to get our largest power of 2. So we'll say int num shifts is equal to test dot largest power of 2 cur mult. All right. Then we need to call left shift over and over and over again on bin num shifts number of times. So we'll say, well, we just do a for loop. For int I is equal to 0, I is less than num shifts I plus plus, bin is equal to test dot left shift bin. So we'll left shift it enough times, and now that's stored inside of bin. Then we're going to take, we're going to return test dot add bins, the new bin, plus what? Test dot multiply. Oh, actually, can we can't destroy bin. Reason we can't destroy bin is we needed 1010 over and over again. So we're going to need a string cur bin is equal to bin here. cur_bin is equal to left shift of cur_bin. That way we maintain our original bin. Then we'll add bin, which is the original, multiplied, actually no, I'm sorry, we'll add cur_bin, plus test.multiply of bin, the original, not times multiplier, but times what? Multiplier is currently a binary number, right? Cur_mult is, actually no, the, where are we? Num_shifts. Num_shifts is the power of 2 that we need. So what we can do is we can take integer.parseInt this guy for base 2 and subtract from that 2 to the num_shifts power and then convert it back to binary. And that's what we're passing in because this guy takes binary. So that is to say if the current value of multiplier was 11, so it'll be the binary version 11. We'll turn it into 11. If our power was 3, that's going to give us an 8, right? So we're going to go 2 to the third power, that's 8. 11 minus 8 is 3. Convert that back to binary, and that's what we'll send into multiplier. The difference between the current multiplier and num_shifts, 2 to the num_shifts power. So let's do solve for new multiplier. So int cur_mult. Let's see. I already have a cur_mult up there. Did I ever use that? I never actually used that. Did I? Where? Oh yeah, hate it. I don't like my variable name for it. Whatever. So we'll call this val integer.parseInt multiplier 2. So that'll turn it into a decimal number. So we need to spell this right. Then int val2 is equal to math.pow to num_shifts. All right, final minute here. And this needs to be a double. This needs to be a double too. What's he complaining about here? Oh, this needs to be a double because this guy returns a double. All right. Then, for our new multiplier, we're going to pass in val minus val2 as a binary number. So, converter dot decimal to binary val minus val2. All right. And it wants this as an int. We know it'll be an int. We'll go over this next time, but I'm pretty sure this is actually working. Just kind of a nightmare. All right, so I think that's a recursive version of multiply. We'll test it next time, but you think? Yeah, it's pretty quick code.